Okay, so let's start. So the speaker is Professor Nick Manton from Cambridge. He's a pioneer of Sphalerons, as you know. So talk title is constructing kinks and Sphalerons in one dimension. So please start.
Thank you very much, Masashi. I think I'll make this smaller. Yes, I think you can see more of my screen. Yeah. Okay. Thank you very much, Masashi. And thanks for organizing this very interesting extended seminar. I don't think we ever had this kind of structure before, with sort of a bit like a conference, but spread out. And I hope it'll be stimulating and people will have time to think about, the various talks and have new ideas during this month. So my talk is concentrating on kinks and sphalerons in one dimension. But since this is the first talk, and I know some of you here are not experts in this subject, I'll give a more general introduction first, and then mention some other examples of solitons, and then go on to the more technical ideas connected with these kinks and sphalerons. So there's an old subject, kinks, particularly kinks. They've been looked at for 50 years or so. There's an old review article and book by Rajaraman, which inspired me when I was a graduate student. So there's a lot of old work. A lot of people have worked on this area, and I won't be able to give full credit to everyone involved. I've written a paper just very recently, which came on the archive only yesterday, and there are more references there. But full literature would be very hard to summarize, and so I'm afraid I won't be able to give credit to everyone who's contributed. So more generally, these topological solitons, they're classical solutions of equations of the field theory. So usually a relativistic field theory, sometimes not, because there are condensed matter applications of solitons, as well as particle physics applications and applications in cosmology. They're usually time independent, at least initially. The basic solitons are time independent solutions. They are localized in space. That's what makes them particle-like, but they're smooth and stable. They're not like delta functions. They're not point-like. They have a finite size, and that makes them attractive as models of particles. And they have finite energy. So, and they model a type of particle, or localized structure, possibly in a condensed matter situation, not an elementary particle. And their existence and stability relies on nonlinearity. The field equations must be nonlinear. If you have linear equations, you tend to get just waves. But this localization depends on nonlinearity. And there are various ways in which that's realized, which I can't summarize here because it depends on the details of the model, the dimension of the model. But one feature of the nonlinearity is there is not a unique vacuum. It doesn't happen always, but very often you need some kind of potential in the field theory, which doesn't have a unique vacuum. If you have a unique vacuum, then the particles are just wave oscillations around that vacuum. But if you have multiple vacua, then you can have structures connecting the different vacua in different regions of space. And that's really what these solitons often are. The nonlinearity can arise because of the action of a symmetry group, spontaneous symmetry breaking. That's also related really to this existence of multiple vacua. And the fundamental field doesn't have to be linear. You don't even need a potential sometimes. You can just have a field which itself perhaps is a linear field, but subject to some nonlinear constraint. And that happens, for example, for skyrmions. You have a field which really has 4 components, but there's the sum of the squares is fixed, which means that the field itself lies on a 3-dimensional sphere. And that creates the nonlinearity even before you write down a Lagrangian or field equation. And it's this nonlinearity that leads to the possibility of topological solitons. Then it's all very dependent on dimension. So my later part of the talk will be on kinks and sphalerons in one dimension, but there are lots of solitons, perhaps more interesting ones, in higher dimension. Now, I'll talk about these one-dimensional solitons, which are kinks, but you can extend the dimension even in a field theory like that by adding 2 extra dimensions, and the kink doesn't depend on those extra dimensions. And then the kink, which is of a localized structure in 1 dimension, becomes a domain wall in 3 dimensions. So it's got an extension in the 2 extra dimensions. And one side of the kink is one side of the wall, and the other side of the kink is the other side of the wall. And the wall itself is a surface in 3-dimensional space. And that's particularly useful in condensed matter context. In the basic solution, the wall would be flat. It would be planar, but then the wall itself can bend and have its own dynamics because of the kink dynamics that creates some kind of non-trivial dynamics for the wall itself. Now, if we're in 2 dimensions, there are sort of several examples of solitons here, 3 of them. It's not quite exhaustive. There are Sigma model lumps, vortices, particularly vortices with magnetic flux, so abelian Higgs vortices, and magnetic skyrmions, which have become very important recently and have applications. Now, anything 2-dimensional, that looks like some kind of localized object in 2 dimensions, some kind of pancake structure or disk structure in 2 dimensions. If you do include a 3rd dimension, then these disks become string-like in the 3rd dimension. And again, the string could be straight, but it can be bent and it will have dynamics of its own. They're true 3-dimensional solitons. 2 examples are magnetic monopoles and skyrmions, the skyrmions that I've been interested in, which represent protons and neutrons and that go back to Tony Skyrm's pioneering work around about 1960. And I call those baryonic skyrmions just here because, so as not to mix them up with the magnetic skyrmions, which come from a different kind of Lagrangian, but have some similarity. The magnetic skyrmions are in 2 dimensions, whereas skyrmions with applications to nuclei are in 3 dimensions. One very important idea in this whole subject is the idea of Bogomolny, Prasad, and Sommerfeld, often shortened to BPS, which you see all over the place in field theory and in supersymmetric field theory. Bogomolny, Prasad, and Sommerfeld, Bogomolny and then together Prasad and Sommerfeld independently studied some aspect of solitons, which was very important in the early days, in the 1970s. And so their ideas have been spread widely, and now one just talks about BPS. What they did really was to realize that for a whole class of solitons, you can reduce the normal field equations, which are 2nd order in space and time derivatives. You can reduce that to 1st order equations, particularly for static solutions. So forget about the time derivatives. If you have static soliton obeying 2nd order Euler-Lagrange equations, then in many examples, interesting examples of field theories, but often with special parameters, you can reduce the equation to 1st order equations. And this helps in several ways. It explains why the soliton is stable, and it helps you to work out the energy. And I'll say something about that for the application to Kinks later on. Just before I get on to Kinks, I'll show some nice pictures I've got of skyrmions. So these are solitons in 3 dimensions. Here's the B equals 1. Oh, B is the baryon number. That's the topological character of the skyrmion. It has an integer characteristic, the topological charge, which is interpreted as baryon number. And it's an integer, can be negative, but here's the positive value. So the simplest one has baryon number 1. It's a spherical object. What I'm showing is sort of where the energy is concentrated. It's concentrated inside some sphere, but the whole field is smooth. There's nothing sharp about this surface. It's just that I've just chosen, or my collaborators have chosen, a particular value of the energy density, and they've shown the surface with that energy density. But the energy density is bigger inside and smaller outside. And the coloring shows the field structure. So skyrmions, like many solitons in more than 1 dimension, more than 1 space dimension, need several field components. So to illustrate the fields and not just the energy, you need some kind of graphical or coloring scheme, some arrows maybe, to illustrate the field structure. So that's what the coloring means. I won't go into the details here. And these solitons can merge into higher topological charges. So here's topological charge 4, barrier number 4 in this application. This is the minimal energy skyrmion with barrier number 4. And you see it can be constructed by bringing together 4 of the simpler skyrmions like this. But as they come together, because of the nonlinear equations, they don't merge in a simple way. The geometry is very complicated of solitons coming together. This is the most compact object you can make from 4 skyrmions. As you see, it has a very interesting shape with cubic symmetry. And here's some more complicated dynamics of skyrmions with barrier number 16. This is really just to illustrate the complications of topological solitons. They are particle-like. They are often simple shapes of spherical in 3 dimensions. But once they interact and you've got lots of them, the dynamics is very complicated, as in particle physics you expect. So I won't describe the details of this. Now, let me give an outline of what I mean by Sphaleron. And so just a reminder, a soliton, a topological soliton is typically a stable object, often minimizing the energy and often satisfying this Bogomolny calculation, which explains, why it's stable. But in field theory, it's quite possible to have unstable static solutions. So these are saddle points of the field configuration space of the theory. So Sphaleron is an unstable analog of soliton. The word Sphaleron comes from the Greek word for unstable. And it's a finite energy saddle point of the field theory. It's analogous to a soliton because it has similar properties in that it's smooth, it's localized, and it has a finite energy. And it tends to the vacuum at infinity, but still locally, it's very much a non-trivial solution. And a Sphaleron usually is sort of defined to be an object with a single mode of instability. There can be easily saddle points with higher numbers of unstable modes, but they are often of higher energy. And so the most sort of important unstable object is the first one you encounter as you raise the energy, and that often has usually has a single mode of instability. So their existence depends again on this nonlinearity, in fact, on the topological structure of the field configuration landscape. So field configuration landscape is the infinite dimensional space of all possible field configurations of finite energy, possibly satisfying some boundary conditions. And that landscape can be complicated. And in a landscape, when you've got a potential energy in a landscape, you can easily have saddle points of, with different numbers of unstable modes. You can understand this Sphaleron existence through a non-contractible path through the landscape, where you start at the vacuum, you travel up to the Sphaleron, so up in energy, and then you go back down again to the vacuum, but in some sense on the other side, so that the Sphaleron is a mountain pass between 2 vacuum configurations. And the 2 vacua could be identical, in which case this path is a closed loop, or it could be or the vacua could be different, in which case you've just got that's more like a landscape in nature, where you go on a road that takes you from one valley to the next valley, but you have to go over a mountain pass to get there. And the mountain pass is itself a stationary point of the potential, but it's unstable. I'll be showing you Sphalerons in 1 dimension, and typically they're not quite independent of kinks. So in theories with kinks, you can also have Sphalerons, and the Sphalerons often look like kink-anti-kink pairs. There may not be a kink in the theory, but sometimes there is. And so you get these pairs, and somehow there are 2 forces acting. So the kink and anti-kink would typically annihilate. That's one kind of force, an attraction. But there could be, if you have some ingredient which creates also repulsion, then the Sphaleron usually exists because the attraction of the kink and the anti-kink is in equilibrium with the repulsion between the kink and the anti-kink. And so there's some sort of unstable point. If they come closer together, they annihilate. And if they get further apart, they split up. So then the pair can annihilate or split up, and you're sitting on this sort of unstable equilibrium. The best known Sphaleron, which I worked on long ago with Franz Klinkhammer, is the Sphaleron in the standard electroweak theory, which has gauge and Higgs fields. So we were motivated by the fact that it was known that the standard model has no monopoles, even though several of us were interested in monopoles. So I was wondering, well, are there any other kinds of solutions that are not monopoles, but are still static solutions? And it turned out there was this unstable static solution, the Sphalerons, and it's got a known energy of about 9 TeV. So it's hoped that it could be produced, but it's very difficult to produce it because it's very small. It's smooth, but it's very small. And it's important because vacuum to vacuum tunneling via this electroweak Sphaleron changes the baryon and lepton numbers. Okay, now to the technical part of the talk and specializing to scalar field theory in one dimension. So we have a single scalar field, so it's rather the simplest case. I mean, the reason for talking about this, and particularly in this first talk, is this is the simplest example of topological solitons. And, you can solve the equations rather easily and explicitly, and the talk will be about that. So you have a single real scalar field, phi. It's a function of space x and position t. X is just one spatial variable. And there's a potential u, depending on just on phi, that provides the nonlinearity. And u could have multiple minima. The minima of u could be not unique, and that can create the possibility of kinks. Then we have a standard Lagrangian for this theory. So you have a kinetic term, the time derivative squared, and gradient term, the space derivative squared, and the potential u, and they combine into the density of this Lagrangian. And then the full Lagrangian is the integral of that over space. There is also an action where you integrate over time as well, but I'm interested really in this Lagrangian. From this, you derive classical Euler-Lagrange equation. There's no hint of quantization here. When you study solitons, you solve the classical equations. There is a whole story then of what is the role of the solitons in the quantum theory, but I'm not going to talk about that today. Maybe some of the other lectures will cover that. I mean, it's an old topic, this quantization. That's Rajaraman's book summarized the basic ideas, but I'm not going to talk about that today. So we just look at the classical equation, and here's the second order field equation. Again, nonlinear if u is anything other than quadratic. So u is not quadratic because that would give a linear field equation. So u is a polynomial, but higher than quadratic, or something other than the polynomial. Now, I'm interested in time-independent fields. It's important to realize that the solutions of this classical Euler-Lagrange equation are fully dynamical and complicated. There are waves, there are solitons, they move, there could be Sphalerons as well. They all move about, they collide. Collisions produce radiation, which is in the form of waves. But I'm going to skip all those non-integrable details and go to the simpler case of just looking at the static objects, time-independent fields. And for that, we don't need the full equations. We just look at the energy, which involves the gradient squared and the potential. And the signs have flipped because it's the energy. So in the Lagrangian, both of them had minus signs. Oh, I should mention this Lagrangian is relativistically invariant in 1+1 dimension. When we look at static solutions, we will have sort of suppressed the relativistic invariance. So here's the energy with the gradient term and the potential term. And the Euler-Lagrange equation for this energy, which gives the field equations satisfied by any static solutions, are these ordinary differential equations, nonlinear ordinary differential equations shown in the middle here. So the double space derivative of phi is half of the derivative of the potential. And that's just the static version of this Euler-Lagrange equation here with the time derivative suppressed. Now, the key thing about this equation, which is not true for almost any other kind of more complicated soliton in higher dimensions, but it's true in one dimension, is that you can always integrate this second order ODE. So you multiply by the first derivative, left and right, and then you integrate both sides. And you get the first integral of the equation, which is shown at the bottom here. It's the first derivative of the field squared is equal to the potential plus a constant. So the constant comes from the integration. Now, for this talk, so don't get confused by this, but for this talk, I'm going to absorb the constant into U. So if the constant is non-zero, then at this stage, you have to redefine the potential to capture C. Now, one doesn't usually do that, but it's very convenient for all the formulae that are to follow. I don't want to have a constant C around all the time. So I'll assume C is absorbed into U. If you like, you can say that C is zero, but you should then allow U to have in it an arbitrary parameter representing this sort of suppressed C. Anyway, so here I'm going to assume C is zero or put C to zero, and then I'm going to take the square root of this equation. So that's just d phi by dx is the square root of U. And I won't be very precise about the sign at this point. Right, so this gives the reduced first order equation. So you just take this equation at the bottom, put C equals 0, take the square root, and you get this first order equation. d phi by dx is the square root of U. So U is some function that's been specified, and now it's actually got this constant absorbed into it. So it's been altered by that constant if necessary. Now, the nice thing about this is that you can always solve it. At this point, the solutions of this equation could be kinks, they could be sphalerons, they could be kink chains, they could have infinite energy, they could have finite energy. All static solutions obey this first order equation. But whether the solution is a kink or Sphalerons depends on boundary conditions and the stability property of the solution. But the thing about this first order equation is formally you can always integrate it. You just separate variables. You have dx on one side and d phi over root u on the other side, and you integrate. So x is the integral of d phi over the square root of u. And what that integral will be like depends very much on the shape of u. Phi is really a real variable, but because of the square root of u, there could be branch points. So the idea is that you start with a variable phi and a phi plane, a sort of complex phi plane where integrals would live. But because of this square root of u, there can be branch points of the square root, and you need to go to the double cover of the phi plane for this integral to always make sense. If you don't consider the double cover, you hit problems, you hit singularities and sign ambiguities. But by going to the double cover, you get really an unambiguous integral here. It does depend on the endpoints, and the different signs for the square root really correspond to different starting and endpoints. So I will actually assume that U is a holomorphic function, so we can talk about this extension to the phi plane. I mean, U will be a polynomial. It'll be a fairly elementary function usually, so a polynomial in phi, or possibly a trigonometrical function in phi, or hyperbolic function in phi. So you can think of U as holomorphic, and therefore this construction of the branch double cover makes sense. Now, these branch points are important, and so they come from the zeros of U. The branch points are where U is 0, or some zeros of U can be branch points. Now, if U only has zeros of even order, i.e., for example, double zeros, then you don't get any branching. Then U will have an explicit square root. So, polynomial can have an explicit square root, which is also a polynomial, and you don't need any more square root signs. But generally, that's not true. And it depends whether the zeros are of even order or of odd order. If they're all of even order, then you can always find an explicit square root, and you can then forget about this branch double cover. But some examples will have simple roots, and some of our examples will have just double roots or higher even order roots. Okay, so we'll come back to that. It's an important aspect of this story. So let's look at some examples, and then we'll start to see illustrations of these sort of double zeros and double zeros and multiple zeros. So the classic example of a kink is the so-called phi to the fourth theory kink. So this comes from the double well phi to the fourth potential. I've got a picture of this in a couple of slides. So U of phi is quartic function, a function that has a maximum power phi to the fourth. So 1 minus phi squared all squared. That's the simplest example of this nonlinear scalar field theory. And you see, I've written out the factorization. So 1 minus phi squared is 1 minus phi times 1 plus phi, and then everything is squared. So you see that there are zeros of u at phi equals 1 and at phi equals minus 1. But because those factors on the right are both squared, these zeros are both double zeros. So it's got two double zeros at 1 and minus 1. I've said that, yeah, it has double zeros, plus and minus 1. And that means the square root of u has no branch points. You can just take the square root. And the square root is obviously just 1 minus phi squared. So the solution of the field equation is x is the integral of d phi over this square root of u, which is 1 minus phi squared. Now, how do you solve that? Well, it is an elementary integral, but let me show you sort of the method, which is you use the method of partial fractions. You know, there are more various kinds of changes of variable by which you can do this integral, but this is, you know, an illuminating method. So this is the method of partial fractions, which can deal with any kind of sort of rational expression in phi. And this quantity 1 over 1 minus phi squared, the partial fractions is 1 over 1 minus phi plus 1 over 1 plus phi. And so you have to integrate that. And now these are linear factors, or, you know, simple partial fractions. And because this is a linear, has just a linear factor in 1 minus phi, when you integrate, you get a logarithm. That's sort of typical. When you integrate a rational function, you will see logarithms. And so, you know, there's a log here and a log here, and you add them up. Well, you actually subtract them because of this minus sign here, and you get, this is the integral. So that is the solution. In fact, this is a kink connecting the points -1 and +1. I'll show you the picture. But you see, it's not in explicit form. It says that x is some function of phi, whereas we really expect phi to be some function of x. That was more illuminating. And this one can be solved. So you multiply by 2, you exponentiate, you get e to the 2x, and then you resolve this sort of factor 1 plus phi over 1 minus phi, and you extract phi. And phi of x is this sort of rational thing involving e to the 2x. And when you simplify this, it's tanh of x, hyperbolic tan function of x. So that's the explicit kink, because you can invert this equation. And tanh x runs from -1 at x is minus infinity to +1 at x equals plus infinity. So it connects these values, phi minus -1 to phi plus equals 1. Right. So that's the classical phi to the 4th kink, tanh x. I've got some pictures now. This is the potential that we started with, this quartic potential with 2 minima, and they're both double zeros. So that's why you get this quadratic behavior. U doesn't become negative. Also important to get the kink connecting -1 to 1 is that u is positive between these zeros, because one takes the square root of u, so that itself is real, positive or negative. And I took it to be positive, I think, this time. And you need it to be positive in order that the d phi by dx is positive. You see, in this equation here, it's important that u is positive for the square root to be real and for the derivative of phi to be real. So phi then stays real as a function of x. All the solutions I'll be looking at, phi is real. So here's the potential, and here's the kink solution. It's this tanh function. Now, the solution I showed was the tanh centered at 0, but actually there's another constant of integration, which I didn't talk about. When you do this integration, there's actually a plus a constant here, and that leads to a shift, potential shift of x. So in all these solutions, there's always a sort of one constant of integration, which represents a shift, a translation of position. And so this picture shows the kink centered at this point, but you can translate it arbitrarily. There's solutions with arbitrary positions for the kink, but it's always the tanh shape. You might wonder, you know, why the solution exists at all in this kind of potential. And there's a mechanical analog, which involves turning the potential upside down. Let me describe it and then I'll show you the slide as well. So you imagine turning this potential upside down, and then you get a potential that goes sort of up to 0, down again, and up again, and down again. And as you see now, suppose you have a particle that starts here, then in this inverted potential, it can roll down and roll up again to this end. And that's the mechanical analog for the kink. It takes infinite time to roll from a quadratic stationary point down and back up again. It takes infinitely long to get there. It takes infinitely long to leave here. And that's the analog of the kink, which just connects here and here and doesn't go back. So here, yes, the solution 5x is analogous to a frictionless point particle motion y of t in a potential v of y. And the standard conservation of energy for the point particle is this equation. That's similar to the kink equation I had this. So to make the analogy, you put E equals 0, this energy E equals 0. And then you see that the important thing is there's a sign change. This V here occurs with the opposite sign to the U that I had earlier. So yes, in this equation, U was on the right-hand side with the first derivative squared. And now it's on the left-hand side. So that's why in this mechanical analog, you've got to change the sign of the potential. There's also a factor of 2 to worry about. So the analog of U is the inverted potential. And that's very helpful thinking about this inverted potential, because you can have a feeling for what kind of motion of a particle is possible. And that immediately tells you what kind of kinks or sphalerons there could be. So the kink profile is equivalent to a particle motion in the upside down potential. And the particle takes infinite time to roll between stationary points. Right, let's go to some more complicated potential. So here's a 1 minus phi squared, but to the 4th power. And the same formal solution exists. X is the integral of d phi over the square root of this, which is an explicit function. So again, we don't really have to worry about any branch points. There's d phi over 1 minus phi squared squared. And what I want to show you here is, again, the partial fraction method. This is, again, a rational function. And you can find the partial fractions for this. And again, factorize into 1 minus phi and 1 plus phi. These, again, this has the 2 minima at phi is plus or minus 1. And you see that in this partial fractions, 1 minus phi occurs and 1 plus phi, but you get a squared term and also a non-squared term, and the same here. So when you start integrating this, so this is the solution, but you've got to do the integral. And that's straightforward. So when you integrate this term and this term, you get rational answers. But when you integrate this term and this term, you get logarithmic answers. So this integral is the sum of a rational function here and a logarithmic function here. And this is a kink solution connecting -1 to 1, but it's rather implicit. Well, it is implicit. It's x is an explicit function of phi, but it's not possible to find phi as an explicit function of x. It's a nice smooth function, and you can plot it, but there's no way of inverting this relation between x and phi because of the combination of the rational and the logarithmic terms. A feature of this is that the potential is much flatter. It's got not double zeros, but quartic zeros, because if you factorize this, you get 1 minus phi to the 4th power. So that's a flatter minimum at plus 1. And then there's also a factor 1 plus phi to the 4th. And that's a flat minimum at -1. And it turns out because of that, this has got long range tails. I'll show you a picture shortly. So it approaches the asymptotic values more slowly. Before I show you the picture, actually I don't have a picture of that example. I've got a picture of this next example, which is a bit similar. Here's another example where you can find the explicit solution, and it's again got these long range tails. So there's a kink. So what's the difference? So I've got the same 1 minus phi squared to the 4th power, but this time I've divided by this 1 plus phi squared. So it's still perfectly real. It's got only 2 zeros at plus or minus 1. This is everywhere positive, this denominator factor. So it's again got quartic zeros at plus or minus 1, and elsewhere U is positive, and particularly between these zeros U is positive. So there's going to be a kink. And the nice thing about this is the partial fractions are simpler. So x is again this you take the explicit square root of this, which you can do, you get this square root and 1 over that, and then you do partial fractions for this. But this time there are no simple pole terms. There's only this double pole at 1 and a double pole at -1. And so when you integrate that, you get a simple pole, 2 simple poles, which you can combine, and that is the solution. X is this function of phi. But now it's invertible because it doesn't mix rational and log functions. So you can easily solve this. It's a quadratic equation for phi. So phi of x is this solution of a quadratic equation, but rather simple. And that's, again, an explicit kink with long-range tails. And here are pictures of these. So here's the potential, the last potential I showed with this, this rational potential. It's got these very flat minima, still got a hump in between. So the kink connects this minimum to this minimum, bit funny shape. And here's the kink, and it's got long range tails. In other words, you see it's approaching the vacuum, this vacuum at infinity 1, and the other vacuum -1, slowly. In fact, like 1 over x, or constant over x. And I call these BPS kinks. All these examples so far are BPS kinks. And the reason I call them BPS kinks is because there's no branch points. You know, in all these examples, I didn't have to worry about branch points so far. Branch points occur if there's some simple zeros in U, but that hasn't happened yet. So I call these BPS kinks. Right, so here's an example. I'm sorry, I think, yeah. Here's an example where there are simple zeros, but they don't really get in the way. This is the only example I show of this. It's the so-called Kristen Lee potential. It was introduced in some paper where Kristen Lee was studying some other things really, but it was an interesting example which they investigated. So here's the potential. It's a sextic potential, right? This polynomial, if expanded out, the leading term is phi to the 6th. And you see, it's got the double zeros at plus or minus 1 as before, but because of this extra factor, this also has zeros, but this has zeros where phi is plus or minus I. So they're off the real axis. You might think they're not important, but analytically they are. For understanding the solution and its energy. And because of these simple zeros, although we'll get a kink, and it's a bit like the Bogomolny, the BPS kink I've been talking about, it has some sort of bit more complication, and I'm going to call them semi-BPS. This is sort of a new phrase that I introduced also with in the last few weeks with also a Polish-Spanish collaboration, and we published a couple of papers in this week on these semi-BPS kind of solutions. The semi-BPS means you get simple zeros somewhere and branching of the square root of U. So you really need to work on the double cover of the phi plane to understand the integrals. So the method works before. X is the integral d phi divided by the square root of U. So here's U. You take the square root. But now you can't just get rid of the square root of this term. So you get this explicit square root, and you need to worry about the branch points at plus or minus I. Well, it turns out this is a simple integral. This is an elementary integral. It's a bit complicated. It's elementary because there are only 2 simple zeros. So the double cover of the phi plane still has genus 0. So when you have 2 simple zeros and you go to the double cover, so branched at those zeros, a double cover of a Riemann sphere branched at only 2 points, is it still a Riemann sphere? In other words, it's of genus 0. And because of that, the integral is elementary. It's sort of well defined on the branch double cover. You can change variables if you like to see that. And it's still an elementary integral. Anyway, I can do it. And it's this slightly complicated logarithm with still square roots in it. And because it's relatively simple, one can invert this. And this is the explicit kink. 5x is sinh of x over the square root of sinh squared of x plus 2. I mean, you have to do a bit of algebra to invert this function and work out phi as a function of x. Well, one can plot this. It looks a bit like the kinks I've shown you before. So I haven't got a plot. Now, I'd like to show you a bit more detail this Bogomolny argument. So I've been talking about this BPS, which base B stands for Bogomolny. So let me just show you how that works, because it gives new insight into all the kinks I've shown you. So the idea is you take the energy function that I started with, but you complete the square. In other words, you take d phi by dx minus the square root of u and square that. And that's called completing the square. But you know, then there's a cross term, which is linear in d phi by dx and linear in the square root. So you get this cross term, the product of square root of u and d phi by dx with a factor of 2. And now you just, the important thing about this is because linear and d phi by dx and you're integrating dx, you can integrate this and get rid of the x integral, turn it into a phi integral. So you get this first term, which is the same as there, but you now get the integral between endpoints, whatever they are, of the square root of u d phi. This factor of 2 cancels against this half. So there's no, that's why there's a 1 here. So you see from this combination that the energy will be minimized provided this is 0. In other words, provided d phi by dx is the square root of u. Then the energy will just be this term. And the nice thing about this term, which are recognized by Bogomolny, is that this is topological because it depends on the endpoints where phi begins and ends, phi minus and phi plus. It depends on the function u, but it doesn't depend on how phi runs from phi minus to phi plus. So you have this function phi of x, but the x dependence doesn't come into this integral. The energy doesn't depend on the shape of phi of x. It only depends on the asymptotic values of phi, phi minus and phi plus. And of course, it does depend on the potential. So if you can satisfy this equation, then this integral is 0, and the energy is just this final integral. And we then say that energy is topological because it only depends on u and the endpoints. And that helps us to work out the energies of all those kinks I've shown you so far. So first of all, we notice that this equation is the field equation I've been solving. So this Bogomolny argument rederives the first order field equation. And notice even the constant c, which I introduced earlier, is now automatically 0 here. That sort of simplifies things. Now, in order just to do the calculation, we define a new function w to be this integral of u, the square root of u d phi, and then so that is just this integral as an indefinite integral. But then you want to evaluate it between phi minus and phi plus. So you need to work out w at the endpoints, and the energy is the difference between the w function at the endpoints. So here's some examples. The phi to the 4th kink, which the first example I gave, the square root of u was 1 minus phi squared. And so it's easy to work out w. You integrate this square root and you get phi minus 1/3 phi cubed. And then the kink energy is the difference between the value of this function at the 2 endpoints. And the endpoints are the zeros of u. So you knew those were plus or minus 1. That's where u is 0. And so the kink runs from -1 to 1, and its energy is w of 1 minus w of minus 1. And from this, you easily find it's 4/3. You can do the same for the, for this semi-BPS Chris Lee potential, its kink, which I worked out explicitly. And, you know, w is this integral. It's the integral, again, of the square root of u, which is this thing with an explicit square root, d phi. Now, this is doable, but it's again complicated, and that reflects the semi-BPS character, the fact that there's these simple zeros, admittedly in the complex plane, and which cause difficulties in the integration. And so it turns out that w is this sort of algebraic function plus this inverse hyperbolic function. So it's sort of mixture of algebraic and transcendental functions. It's elementary, but it's also transcendental. And now it's easy to work out W at 1 and -1 as before, and the difference is this transcendental number. So you can calculate E, but it's this funny combination, and that's characteristic of the semi-BPS solutions. I mean, sometimes these integrals won't be possible at all. They'll be elliptic integrals with some parameters, and you won't be able to find any kind of explicit way to write them down. So that's characteristic of the semi-BPS kinks, whereas the BPS kinks, involve rational integrals, which are easier. Right, it's time to move on to a Sphalerons example, and I explained sort of generally what a Sphalerons was, but now let me give you just the basic example in one dimension. So for this, you need a cubic potential. This is the simplest case, phi squared times 1 minus phi. This again has a double zero at phi equals 0, but the important thing is it has a simple zero at phi equals 1, a real simple zero. And because of the simple zero, u becomes negative if phi is bigger than 1. The Sphalerons solution can still be found. I mean, first of all, formally, it's x is the integral of d phi divided by the square root of this. And now, because this is a simple zero, inevitably there's an explicit square root symbol, and inevitably then the solution we'll call semi-BPS. Now, what is the solution like? As when you do this integral, what happens is that phi runs from a double zero at phi equals 0 to the simple zero at x equals 1. But that happens, it reaches phi equals 1 at a finite value of x. So if you only integrate between 0 and 1, x will only have a limited range. A sort of half interval, half the real line will be covered if you just integrate from here to here. That's no good. We want to cover the whole real axis in x. And you do that by going back to the starting point, phi equals 0, but on the second sheet of this double cover. So you go round in this integral, you go round the branch point at phi equals 1. So this integral should be thought of as the integral between 0 and 0 in phi, but starting on the first sheet, going around the branch point at phi equals 1 and going back to 0 on the second sheet. And the Sphalerons is semi-BPS because of this branch structure. You can still do this integral. If you choose this parameterization, phi is 1 minus t squared, you find that this integral simplifies to something rational. And the important point here is that when phi equals 0, t is plus or minus 1. But when you do the change of variables, the thing you notice in this sort of contour integral is that t starts at -1 and it ends at +1 because you go from one sheet to the other sheet. So t doesn't start and end at the same place, it starts and ends at different places. And that's useful because otherwise this integral will be trivial. Anyway, it's not trivial, and you get 2 tangent inverse of t from this integration. But so inverting this, t is tangent of half x, and phi is 1 minus t squared. So 1 minus tangent squared, so 1 minus tangent squared half x, here we are. And this simplifies to 1 over cos squared half x. So that's the solution. I'll explain why it's a Sphalerons in a moment. I've also got some pictures, so I'll come back to those. So the Sphalerons energy is still given by this Bogomolny formula involving this W function. So you find the integral of root u, that gives the W function, and you integrate over the phi contour. You've got to be, again, careful about the branch point. You've got to go around the branch point. You can change variable to the t parameter, which I did here. I mean, this change of variables. And then the t integral is from -1 to 1. And so you end up with a non-zero result for the energy. The energy is 8/15. And it's positive. that means it's higher than the trivial solution where phi is 0 everywhere. Now, why is the Sphalerons unstable? So here's a remark about Kinks solitons and these one-dimensional Sphalerons. As I mentioned, both of them have a translation 0 mode. In other words, although I suppress this constant of integration, all of them can be translated. You can shift x by a constant. And if you do that, if you do that infinitesimally, you call that the translation 0 mode. It's 0 mode, zero is short for zero frequency mode. If you study the small oscillations around a kink or a Sphaleron, which require you to start with the second order full dynamical equation and then linearize. So you look at sort of small oscillations around the static solutions. Then you can look at the frequencies of the modes of oscillation. So which are, these are the eigenvalues of some operator, second order Schrödinger type operator. Now, one of these modes is always the translation 0 mode. That's got 0 frequency. That's a small deformation of the soliton or Sphaleron, where you just translate it infinitesimally. And that's always got 0 frequency because the energy is unchanged. Now, the Sphaleron translation mode has a 0. So because the solution, I haven't shown the solution. Let me show you. Here's a solution. This is the Sphalerons solution of the example I gave you, the 1 over Cauchy squared function. Now, if you translate this a little bit, the translation 0 mode is just the derivative of this function. That's if you change its center slightly, the change of the field is the derivative, and that change of derivative. That derivative of this function is positive here and negative here and is 0 there. It's got the derivative has a 0. So for this Sphalerón, the translation 0 mode has a 0. In other words, it's got a node. And by the sort of general theory of second order operators and their spectra, if one of the modes has a 0, then there's a lower frequency mode with which is node-less, doesn't have a 0. So the Sphalerón second variation operator has a nodeless eigenfunction with a negative squared frequency, and that's the unstable mode. So because the Sphalerón solution has a maximum where the derivative is 0, the Sphalerón is automatically unstable. A soliton doesn't have this property. So the picture was remind you of a picture of kink. Here's a kink. Here the derivative is everywhere positive. And therefore when you think about this second variation operator, the translation 0 mode is the lowest mode because it's got no zeros. And so this object is stable. It's got no negative frequency mode. But because this Sphalerón has a maximum where the derivative is 0, it's unstable. Sorry, I put these pictures a bit in the wrong order. Here's the potential that I started with to get the Sphalerón. It's got the double 0 at the origin, and it's got a simple 0 here. And so the potential goes negative on the right. And so this is, because of this is called a false vacuum, because if the field is sitting here, it could sort of tunnel down to this negative energy world. And the tunneling is via the Sphalerón solution. The Sphalerón goes from here to the simple 0 and back again. So again, think of this inverted potential, a particle rolling the inverted potential. It rolls down, it goes to the simple 0. In a finite time, then it turns around and goes back and comes back to the starting point. So this rolling particle is useful for understanding why the solution exists. And here is the solution. It sort of rolls from 0 up to a squared and back again. Oh, I think I've got an a squared here, whereas in the, oh, sorry, here I put a squared equals 1 in the, so a squared is 1 in this formula, but I left it as a squared in this picture, sorry. Okay, I'm running out of time. So, but there are further solutions in which if U has adjacent simple zeros. So, and these give kink chains. So we've had, so far we've considered double zeros, we've considered a double zero and a simple zero, but another possibility is that U has two simple zeros that are adjacent to each other and U positive between them. And then there's a solution that goes from one zero to the other zero in a finite range of X. X increases over a finite range between these zeros when you solve the equation. And so you have to extend X and it goes round the branch points. So because of the simple zeros, there are two branch points at these zeros. And the solution is a sort of contour integral going around these branch points again and again, round and round and round. X continues increasing on the second sheet of root U, then it goes back to the first sheet, then it goes to the second sheet, the first sheet. And the result is that phi of X is spatially periodic. It's a chain of alternating kinks and anti-kinks. Sort of kink when it goes one way and anti-kink going the other way. And like a Sphaleron, a kink chain is unstable for the same reason to do with looking at the translation zero mode. The translation mode has lots of zeros, and so therefore there are negative frequency solutions for this oscillation problem. Here's the simplest example that has this kind of simple zeros. Phi, U of phi is just 1 minus phi squared, very simple quadratic function. This is a bit artificial, this example. The kink chain, which solves this, is just a sine function. It oscillates between -1 and 1 with period 2 pi. It's a periodic structure. And where it goes up, you call that a kink, and where it goes down, you call it anti-kink. This is not very realistic because this potential is not very realistic. More realistic is if you have a quartic function. And this now has 4 simple zeros, but and so the integrals get more complicated. They are now elliptic integrals, and there is a solution, but it's an elliptic Jacobi function, Sn of x, which is in some limit becomes the sine function. It still oscillates between plus or minus 1. I've put k here to be less than 1. So it still oscillates between these zeros, the zeros of this bracket. So typically kink chains are involve elliptic or hyperelliptic integrals. They're more complicated analytically, and also they're semi-BPS because you need these simple zeros. You need these branch points, and there are quite a lot of them. Here's another realization of this theory to trigonometric potentials. I don't know if you can see this. It says U is cos to the n of phi. Can you see that, or is it covered? Anyway, so for n equals 1, you get this integral, and that's a rather nasty integral, but it's another elliptic integral. So the kink chain is a Jacobi type function. It's actually a ratio of Sn and Cn functions. For n equals 2, it's simpler because you get this integral, x equals d phi over cos phi, and that can be solved. I mean, that can be integrated, and you can invert the solution to get tan phi is sinh of x. And this is an important example. This is an variant of the Sine-Gordon kink. So Sine-Gordon theory has a potential cos squared phi, or some shift of that. So here's a summary. We found a broad range of static solutions in one-dimensional scalar field theories, kinks, which typically connect double zeros, Sphalerons or quartic zeros, Sphalerons, which connect double zeros to simple zeros and back again, and kink chains, which connect simple zeros of the potential and go backwards and forwards infinitely often. Some of these are stable, some others are unstable. But there are two simple formulae which I've used all the time, that x is the integral of d phi over the square root of the potential. So the solution depends very much on the nature of this integral. And then when you've got a solution, the energy is the integral of u itself, sorry, the square root of u itself between the endpoints. And the endpoints themselves depends on studying the zeros. I mean, these endpoints are always zeros of u. You've got to be careful to choose them, which ones you're talking about. If the integrals are on the phi plane, in other words, if this square root explicitly exists without any square roots remaining, then you call the solution BPS, or we have recently. If, on the other hand, you have to go to the double cover for this to make sense, then we now call the solution semi-BPS. And so the reason is that the energy is not necessarily minimal anymore. You can have Sphalerons, kink chains, which are not stable, and still solutions of this first order equation. And the calculations are altogether trickier because of these simple zeros and the branch points and possibly elliptic functions or worse. So that's really all I have to say about solutions, but I just mentioned they're all part of these static solutions of various kinds. But I want to just remind you that they're all part of a much more complicated dynamical story. The solitons can be moving, you know, moving kinks, moving Sphalerons, although they're unstable, so they don't necessarily last long. There are forces between them. You can have kinks and anti-kinks attracting each other. The kinks themselves can oscillate. I've talked about the deformations of kinks and Sphalerons and the frequencies of the various deformation modes. Some of them can be positive frequency oscillatory modes. So you can have oscillating kinks or oscillating Sphalerons. They can be unstable. And then, you know, to use this theory further, you have to think about kink quantization, Sphalerons quantization, tunneling, and there are all kinds of potential physical applications in condensed matter and particle physics, but this talk has no time for any of those. And here are just some references to this whole subject. It's a very big subject. Many people have worked on it, so this is very incomplete. But I've written a book with Paul Sutcliffe, Topological Solitons, which is now not particularly new. Yasha Schneer wrote another book, Topological and non-topological solitons in scalar field theory. So there's a lot there about kinks of various kinds. Both of these are CUP, Cambridge University Press books. I've written a very recent paper, which is just on the archive, only yesterday, which basically is about on which this talk is based, and you know, has quite a lot more details, one or two more examples, and lots more references to the literature. And so I can't do justice to the literature. There are numerous papers, starting with work of Skirm, who introduced the Sine-Gordon model with his collaborator. There was work in the 70s summarized by Rajaраman in his review article and his book, which I still recommend. Lower did very nice work on a phi to the 6th kink for the first time. Gonzalez studied, with collaborators, studied sort of a tilted phi to the 4th potential with a kink anti-kink Sphalerons. Bazea has written lots of papers with many collaborators on various sort of exotic kinks, particularly with these multiple minima, not quadratic minima, but quartic, sextic minima, and so on. And Kare and collaborators similarly, Gandhi and collaborators similarly. And they've studied not just static solutions, but they've done a lot on the dynamics of these objects. Tom Romanciukiewicz, I've collaborated with. He's part of a large group of Polish, also Spanish group, who worked on all kinds of kinks, studying kinks and Sphalerons and oscillons. I wrote a paper with Tom on oscillons related to a Sphaleron. So we studied this cubic Sphaleron in particular, which I showed today. So they have many collaborators, and there are many others who worked on this. So sorry to all the people whose names I haven't given. I think that's it. Thank you.
Thank you very much for very clear and interesting talks.